Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. How can we approximate continuous functions with polynomials? That's the question of today's presentation. I'm going to show you an amazing theorem by a mathematician called Carl Weierstrass that answers this question. And I'll talk about the proof. And in fact, I'm quite excited about the proof because it's the simplest proof that I could find. Now, this presentation is suitable for someone who's done, say, a first course in calculus, including high school students. So I hope you enjoy it. One of the motivations for putting this presentation together was I used the result that I'm going to show you in my own research. So let me know what you think and let me share my screen with you. Weierstrass and his polynomial approximation theorem. So the first question is, who was Weierstrass? Well, I am glad you asked. Carl Weierstrass was a mathematician in the mid to late 1800s. He got famous around 39 or 40, so he came to mathematics quite late. And he did amazing stuff, including giving a precise definition of continuity and this particular approximation theorem that I'm going to share with you. Now, Carl Weierstrass is one of my heroes. He had a very interesting life too. At university, he skipped lectures, he got into fights, and he drank way too much, and he dropped out because he was studying something that he wasn't passionate about. Anyway, he returned to mathematics and made some amazing contributions. And like I said before, he's a bit strange because his best work was done after he was 40. Okay, so what is this Weierstrass approximation theorem? Here's the result. One amazing theorem of Carl Weierstrass is the following. Suppose f is a continuous function on some closed and bounded interval. We can construct a sequence of polynomials, just humble polynomials, that approximate f in the following way. Give it any positive value epsilon. There's an integer big N such that for all points in the interval, we can make the distance between the sequence of polynomials and the function as small as we like when n is sufficiently large. Now, that sounds like a real mouthful. But what does it say? Basically, it says the following. It says that if you've got a continuous function on a closed and bounded interval, you can approximate it with polynomials to any accuracy you like. That's an amazing result. Okay, so in the language of analysis, what this means is basically the sequence of polynomials converges uniformly to f on the interval AB. Okay, why do I love that result? We're using humble polynomials to approximate all sorts of potentially crazy continuous functions. That's amazing. Now, another good thing about polynomials is that we understand them. They're reasonably simple, and they're differentiable, continuously differentiable functions. Amazing stuff. So what about the proof? Well, for years I've looked for the simplest proof of this result because I was curious about it myself. And I can share a proof due to a mathematician called Jackson from the 1930s. So let's talk about the proof of this result. All right. So the proof due to Jackson. Okay, so I'm going to go through the proof now, and this will take up the rest of the video. So just assume without loss of generality that A and B lie but strictly between 0 and 1. All right. Now, we can extend out the domain of f to the whole real line by defining, I know this is a little bit of abuse of notation, but you define f in the following way. All right. So this looks quite complicated, but essentially it's f for x between a and b. You draw a line joining the endpoints to the x-axis, and it's 0 everywhere else. So if I was to draw a little picture, okay, let's say that's 1, and there's 0, and the function might look like that. Okay. Oh, sorry. Let me make that. Oh, hang on. Let me try that again. Okay, let's say A is here, B is here, and 1's here. Okay, and here you've got your function, your continuous function. So outside of that, you just draw a straight line segment down to 0 at both endpoints, and then outside of that, you make it 0 everywhere. Okay, so that's your function. That's a graph of your function here. Okay. All right. So, okay, so forget about that. All right, so f's continuous on the whole real line. Great. All right, so how do we build this magical polynomial? How do we actually construct it? Well, that's the part of the next proof, the next part of the proof. Okay, how do we actually construct it? And essentially, it just involves integration. So we're going to define a sequence of positive constants by this, I guess, sequence of integrals. Okay, this is called a this is called a Landau integral, if you like, or a Landau sequence. And now Jackson defines his polynomial in X in the following way. Okay, so basically, all you've done there is you've replaced u with t minus x, and you've put in f of t, and the j of n is just down here. Now, it's not too hard to show that this definition for your polynomial is, it really is a polynomial in X of degree at most 2, n, and it does have constant coefficients. Okay, so we're going to work with that. All right, so what we want to do is we want to show that this is true for every epsilon and for n sufficiently large on this interval. How do we do that? Well, what we're going to do is refine our polynomial just to put it in a sort of a slightly more convenient form. And essentially, you can use the properties of the f that we just defined, okay? Because it's 0 outside this interval, we have for all x in this interval, this becomes this. Now, what we've done here is so from this line to this line, all we've done is written the integral in this sort of way. Okay, now in this interval f0, so you're not actually changing this at all. This is just so we can do a substitution in the next line and get a more usable form. So it's a little bit sneaky. Okay, so from here to here, we've used this substitution. Okay. Okay, so hopefully you're following along. There's a little bit of high school integration and substitution going on there. Okay. Sorry, that should be a 1 down there. Okay, sorry, let me fix it up. So that to that, that to that, and then that to that. Okay. All right, so we've refined our polynomial a little bit more. What do we do now? Well, let's actually show the approximation. So let's look at this difference. It's this. Okay, so just from here, it's this minus that. Now, we can replace this with this because you can see here, this integral doesn't depend on x at all. So you can actually put that out the front if you like. And j sub n, well, the Landau integral is just this. So you can divide both sides by j sub n, so you get 1 on j sub n equals 1, and multiply both sides by f of x. That's where this comes from. So we replace this with this and just put it all under the one integral sign. Okay. All right, so let's continue with this. What we're going to do essentially is take the absolute value of both sides and work with this difference here. We're going to put some estimates or some inequalities on the absolute value of this difference. Okay, so that's the next part of the proof. Okay, well, let epsilon be positive, and we're going to relate the epsilon back to this epsilon from the theorem. Our f is continuous, right? So by the definition of continuity, we can always find a delta that depends on epsilon, such that this difference can be made as small as we like, as long as u is small. Okay. Now also, let's have a look at the absolute value of a function f. You can see that f's continuous here, and it's continuous everywhere, and it's bounded, and 0 out here. So you're definitely going to have a maximum of the absolute value of f. Okay, so this m is defined to be the maximum value of f. Then this difference, absolute value of this difference, has to be less than or equal to 2m, and that's not too tricky to understand. This thing is just less than or equal to f of x plus u plus, sort of like a triangle inequality. Okay. Okay, so that's not too bad. So that's true for all u. So for u in here, we have a bound for this difference. For u out here, we can just rearrange this and square. We have this. So definitely, working it up here, this is going to be less than or equal to this, because u squared on delta squared is greater than or equal to 1. So we basically got this, and we've got this. Okay, so no matter what, this difference is less than or equal to this or this. So it's got to be less than or equal to the sum of these two things. Okay, the difference of those of f of x plus u minus f of x absolute has got to be the difference, has got to be less than or equal to the sum of epsilon on 2 and 2m u squared on delta squared. All right, so we can use that and form the next line. For all u, we have an inequality like that. Okay. So remember, we're trying to work with this now. So if we take the absolute value there and put it in there and move it inside and put in the inequality sign, this first part, the first part of this can be bounded by the epsilon on 2, and you've got the 2mu squared on delta squared. Okay, so this can come out the front. You've got 1 on jn times jn, so that'll give you just epsilon on 2 here, and then you've got this, the m. This can come out the front. Okay, and you've got this. All right, so we're making progress. The last thing is just pretty much just to tidy it up. I've introduced this I sub n to denote this sequence of integrals, and what I'm going to do is relate I sub n to j sub n and try to get this to be small. Okay, less than epsilon on 2 for n large. All right, so if I define I sub n in this way, what can I do with this? Well, believe it or not, it's just integration by parts. Yep, integration by parts. So if I write the squared, u squared as u times u, and say that's my v dash in the integration by parts formula, okay, then the first part of the integration by parts formula gives you 0, and the second part gives you this. This can come out the front, and what's left is j sub n plus 1, the Landau integral j sub n plus 1, right? Now, you can show that j sub n plus 1 is less than or equal to j sub n. It's not too hard to actually establish that. And so you can now form an inequality on I sub n with j sub n. Okay, so well, so what? Well, let's look back at the previous page. I can now form an inequality on the I sub n in terms of this thing. Okay, so let's do that. Let's do that. Okay, it's the final step. This now, you can put an inequality there. You can replace it. The j sub n's will cancel. So the j sub n and the I sub n will cancel off. And you're left with this. Now, this can be made as small as you like for n sufficiently large. So there is a big N such that for all little n, bigger than the big N, this will be as small as we want. So we can make it, say, less than epsilon 2. Add these two together, you get epsilon. So this is for all n sufficiently large, okay? Now, notice that we've shown the approximation or the convergence, if you like, on this bigger interval 0, 1. So it's definitely got to work for the interval a, b, which is contained in that interval. Okay? Whew. All right. That's a interesting, a long proof, but can you see how it just uses ideas from a first course in calculus? Integrals, integration, inequalities. Okay, the only tricky thing there is the concept of convergence. Okay, that comes later in a university course. But this, the Jackson's proof, is the most simplest proof that I've been able to find. Okay, so should we run through it one more time just to summarize the points? Let's do that. All right, the theorem is here. We construct a polynomial. Let me just, using what's known as a Landau integral and this thing here. Then we refine the polynomial. Okay, we refine our polynomial by making a substitution. Okay, and using this sort of thing. All right. And then you look at the difference of these two things and put it all under one integral sign. And then it's all about working with this difference here. Okay, one's due to continuity, the other one is due to the maximum. Okay, and lastly, you tidy up with an inequality on this integral here, and you can get the approximation. Okay, in the final step. Okay, what do you think? I think it's an amazing result. Weierstrass just had so many fantastic results that are used 100, 130, 140 years later. Okay, I use them in my own research. I think it's amazing. I also like it that Carl Weierstrass was a bit of a rebel. Okay, he was studying finance at university. He didn't like it. He loved maths, so he got into fights and missed lectures and drank too much. And eventually he found his passion. He went with his dream. That's something that I also respect. Anyway, what do you think? What mathematicians inspire you? If you have any comments, any questions, put them in the comment section. Thanks for watching, everybody. We'll see you soon. Bye.